Hello, we're still in Chapter 3, Logic, but we're going to continue working on truth tables. This time, in Section 3.4, we're looking at truth tables for the conditional and the biconditional. Our objectives are to understand the logic behind the definition of the conditional, to construct truth tables for conditional statements, understand the definition of biconditional, construct truth tables for biconditional statements, and determine the true value of a compound statement for a specific case. Recall what a conditional statement is. It looks like this, where you have P with an arrow pointing toward Q. P is the antecedent, Q is the consequent. A conditional is false only when the antecedent, or the first part, is true and the consequent is false. So, resorting to our truth tables, we have P and Q listed with all the possible values they can have. And so we see that P, if and only if Q, would be true where both are true. It would be false where P is true and Q is false. It would be true where P is false and Q is true. And it would be true where both are false, because the conditional is false only if the first part, the antecedent, is true and the consequent is false. So we see we just have one instance of that in our truth table. In this example, we are going to construct a truth table for not Q, if and only if not P. So as we did before, we list P and Q. We're also going to list not Q, which means we just take the negation of all the values of Q. We list not P, taking all the negations of P. And we see that when we apply our definition, that the conditional is false only when the antecedent, which is the first part, is true and the consequent is false. So the antecedent this time is not Q. The conditional is false only if the antecedent is true and the consequent is false, which is the second line of the table. All the others are true. More on the conditional statement. You can reverse and negate the antecedent and the consequent, and the statement's truth value will not change. If you're cool, you won't wear clothing with your school name on it. If you wear clothing with your school name on it, you're not cool. If the fashion tip above is true, then so is this. And if it's false, then this is false as well. So, dealing with example 2, we want to construct a truth table for something that's a little more complicated. Notice that we're using brackets as well as parentheses for our grouping symbols. So we see, though, that we're only dealing with two simple statements, P and Q. So we list P and Q. Looking inside our brackets, we start with the innermost part, which would be the part inside the parentheses. So we have P or Q. So the second column is P or Q. Notice that if both are true, P or Q would be true. If either part is true, then P or Q is true. But if both are false, then P or Q would be false. The next part inside the brackets is the not P, so we have to find not P, which is the negation of P. So now we've got our part inside the brackets. That is our fourth column. We have P or Q inside parentheses and not P. So looking at columns 2 and 3, we see that the and is only true if both are true, which is our third row down. We're just about ready to do the last part. Now we're ready to combine this with if this, then Q. Okay? So remember that the conditional is false only when the antecedent is true and the consequent is false. So the antecedent is true, and then looking back at Q, the consequent is true. Okay? All the others, the antecedent is false. So it doesn't matter what the consequent is, the whole thing is going to be true. Now we have biconditional statements, and this is where you have the arrow going both ways. P if and only if Q. So it's P if Q and Q if P. Excuse me. This is true only when the component statements have the same truth value. So the truth table for the biconditional, right, we're listing our P, we're listing our Q. So it's true only if they have the same truth value. So the first row would be true. The last row would be true. But for the other two, it would be false because the simple statements do not have the same truth value. Okay, we're looking at definitions of symbolic logic again. We've already discussed these in a previous section. Negation is not. The negation of a statement has the opposite meaning as well as the opposite truth value. Conjunction, which is the and. The only case in which a conjunction is true is when both component statements are true. For the disjunction, or, the only case in which a disjunction is false is when both component statements are false. So for an or, if either part is true, it's going to be true. Conditional, which is the arrow pointing to the right, if then. The only case in which a conditional is false is when the first component, the antecedent, is true, and the second component, the consequent, is false. And biconditional, which has the arrow going both ways, if and only if. The only cases in which a biconditional is true are when the component statements have the same truth value. You need to remember this slide. This is really important for the rest of the chapter. So now we're going to look at a third example, determining the truth value of a compound statement. You receive a letter that states that you have been assigned a super $1 million prize entry winner, 6655671010. If your number matches the winning pre-selected number and you return the number before the deadline, you will earn $1 million. Suppose that your number does not match the winning pre-selected number, you return the number before the deadline, and only win a free issue of a magazine. Under these conditions, can you sue the credit card company for making a false claim? Good question. So, as we have done before, we're going to assign letters to these simple statements in the claim. P would be that your super $1 million prize entry number matches the winning pre-selected number. Well, this is false. It said that it did not match. Q, you returned the number before the stated deadline. You did, that's true. R, you win $1 million. This would be false because it's if and only if. And so the only case when this is true would be if both had the same value, both P and Q. So to make matters worse, you were duped into buying a magazine subscription. All right, now we're going to write the underlying claim in the letter in symbolic form. which we kind of already did. If then is the biggie. So your number matches the winning number, which is P, and the symbol. You return it before the stated deadline. Okay, that is all combined, and so we're going to include it in parentheses. We have the then. You win $1 million, which is R. So we are going to substitute the truth values for P, Q, and R to determine the truth value for the letter's claim. All right, so we have the symbolic statement. We know that P is false, our numbers didn't match, and Q is true, R is false, we didn't win the $1 million. Well, F and T, all right, for an and, a conjunction, if either is false, if they are not the same, then it's going to be false. So we replace the parentheses part with false. If false, then false, which is true. Our truth analysis indicates that you cannot sue the credit card company for making a false claim. And that concludes this section.